Hey, we're here with our kid from the shout-out land.
Yo, chemistry rocks!
All right, that would be Mr. Timothy Woods.
Yeah.
Sharing with this. And, of course, this is Mr. Bergman and...
Mr. Sam's the poet.
The poet?
Yes, remember I'm becoming a poet.
You are a poet and you didn't know it.
Okay, here's my lead poem.
Lead. Well,
Lead.
That's PB, isn't it?
Yes, you bring such pain, lead, fired from a gun. You pierce flesh, deteriorating from many years of exposure. My hair, my skin, lead, keeping Superman from seeing through. Lead, so heavy you are my burden. In my pipes and in my antique plates you haunt me, you weigh me down. Lead.
Oh, I like that. There's
Isn't
the
that nice?
Superman. That's kind of like me, you know?
What?
I'm Superman.
Oh.
You didn't know I was Superman, huh?
No.
Well, you know, I kind of tried to keep it a secret.
Oh, okay.
Yeah, I knew that. So there's Superman.
All right. Well, I guess you do wear tights like he does.
I do wear tights. I do wear tights. Man in tights. I sometimes get strange looks. You know, I'm a cyclist. I'm in internet land. Yeah, okay, we just won't go there. All right, so we are going to start with talking about how to calculate strong acids and bases. So here we are, trying to find the right screenshot. There we go.
There it is.
Hey, strong acids. What's true about all strong acids, Mr. Sam?
100% dissociation.
You know, it's kind of like high school romances. What
It
happens
is.
to all
They
high school romances?
all break up.
Did you guys know that all high school romances break up? All of them? Don't.
Except for like the 0.001%.
Yeah, I think it's 0.001.
And that's about how it is with strong acids or so.
So it's actually kind of perfect here. So what we're trying to do is find what is the pH when you have nitric acid solution. Now, what do you know about nitric acid?
It's strong acid.
So if I had a strong acid, that's like HNO3, and it completely dissociates into H positives and nitrates. So this arrow right here, this arrow is in one direction. Hey, I love the music. How cool is that? Okay, rock and roll. Woo! Actually,
Yeah.
it is a good song. Rock and roll, it soothes the soul. I love this song.
Mm-hmm.
Days of old.
Can you tell we're doing this in the
That
middle
old
of school?
time of rock
today?
and rolls.
Those of you who are not our students, they do this 1 minute before class starts. We get to listen to some music.
Oh, I like this
So
song.
if you're our
Soothes the
student,
soul.
fast forward, about another 30 seconds or so, and the song will be over.
So, yeah, sorry about that, folks in internet land.
Did forget a negative sign on your nitrate, however.
Oh, I did, yes. So, all right, let's put a negative sign right
Yeah.
there. All right, music can end now. We'll wait. But
Anytime.
it does add some ambiance
It is.
to
It's
it.
nice.
I like this music.
Should I dance now?
That would be painful.
It would be quite
You
painful.
might fall and hurt yourself.
Yeah, I probably would.
Yes.
It's a good thing this isn't a video of me podcast.
That's true. They don't
that'd be
have to see
sad
our
and
ugly faces.
Hey, speak for
And
yourself.
now we're going to have like a beep, I'm sure.
There it is. Hey, okay, moving on.
Okay, so if you have a 0.10 molar solution of nitric acid,
Uh-huh. After dissociation.
how much of this is going to go away?
all-
You can actually do
We
like
could
an
do like a
ice
little
table.
ice table or BCA table. Yeah, exactly. We're going to lose 0.1 and end up with
all
0.
of it goes away. And how much hydrogen?
All of it.
Well, it's 0.1.
Yep.
And actually, this
We
is
could do
0.1,
nitrate too, yeah.
but we don't care.
No.
Because it's asking for the pH. And
Yeah.
what is pH?
Negative log of concentration of hydrogen ions.
So that's the negative log of the concentration of the hydrogen ions.
Yep.
Well, that's just going to be the negative log of what?
0.1.
Now, do you need a calculator or something?
Not really, no, because 0.1 is 1 times 10 to the negative 1, and so that would mean my pH is 1.
Yeah. So pH on this one is very simple. It's 1. We didn't need a calculator on that one.
Nope.
Are we good or what?
Mm-hmm.
All right. Conversely, we can also do a solution. Now, actually, this is now a weak acid, though, right?
No, that's a strong.
Oh, it's
Perchloric?
pardon me, it's perchloric acid. I knew that. I was testing you. Yeah.
I know.
So perchloric acid, you could do this, HClO4, and of course that also completely dissociates into hydrogen, and now the perchlorate, ClO4 negative. And so the hydrogen ion concentration, since it completely dissociates, is this number right here,
Yep.
1 times 10 to the minus 10th. So you would, of course, say that the hydrogen ion concentration would be what?
1 times 10 to the negative 10.
It would be equal to 1 times 10 to the
And
minus
if you take
10.
negative log of that, you get a pH of 10. Now that's kind of
pH
weird.
of 10. That should be the answer, right?
It should be, but
This is not true!
no, because it's an acid. You cannot have a pH greater than 7 if you have an acidic solution.
How do we do this, Mr. Sam?
Well, we have to think about what the major species are in there. And if we think about the major species in our water, we have to remember that water self-ionizes. And that in pure water, the hydrogen concentration is 1 times 10 to the negative 7. Which is greater than 1 times 10 to the negative 10, meaning the water is acting as more of an acid than the perchloric acid.
So actually you would say that the hydrogen concentration would be equal to 1 times 10 to the minus 7th plus 1 times 10 to the minus 10.
Right.
We have two sources of hydrogen.
Yes.
The dissociation of the water, which is very rare that this becomes an issue.
Yeah.
And the dissociation of the perchloric acid that's very, very dilute. And so if you were to add these numbers, I bet I can do this in my head. It's about 1 times 10 to the minus 7.
Mm-hmm.
Because you see this 10 to the minus 10th number is infinitesimally small compared to the 10 to the minus 7.
Right. 10 to the third times smaller.
So the pH is
1,000
actually
times less.
very simply
Yep.
7.
Ding.
Not technically, it's actually 6.998 probably, or something very,
Probably.
very small. But for significant digits, actually I've messed up my significant digits. We would say 7.0 because we want to keep a 1 significant digit decimal after, as we talked about last time. Okay, good. Hey, now let's talk about weak acids and weak bases. Now, with a weak acid, they have this thing called the equilibrium constant. The acid equilibrium constant, it's the Ka. And here are the values. Notice something about those values. What do you see about all those values, Mr. Sams?
They are all less than 1.
Yeah, they're all tiny numbers. The biggest number is 10 to the minus 2, and the smallest number is way down 10 to the minus 10. And this is, of course, not an exhaustive list of acids, but it's a partial list.
Yeah.
It's good enough. So now, when we work with these, we have to work with equilibrium constants. And so now let's work a problem. Hey, we have a...
That is not an equilibrium problem.
This is actually a not... Okay.
This problem right here.
Yeah, well, I guess we will...
We're
out of order. We're slightly out of order. This will
we
come
should have set the table about 2 slides later.
This is going to come a little bit later, but we'll talk about that. We did.
Put that in the back of your brain.
Put that in the back of your brain cells. All right, now we have two strong acids. We have nitric acid and we have hydrochloric acid. It's asking what's the pH of the resulting solution. This is a pretty tricky question,
actually.
A
little bit, but this is a good AP question too.
Yeah, AP class. We should probably have AP questions. Okay, so what we've got is we've got two strong acids. So what would be the molarity of this acid?
That one is 0.00125 molarity,
Sort of.
but we need to do an M1V1 equals M2V2 problem
Let's
because...
think this through. I've got two beakers. One's filled with nitric acid, and it's like 54 milliliters, right, from the problem. And another beaker is filled with hydrochloric acid, and I have 25 milliliters. But what I'm going to do is I'm going to pour them together into one beaker. Now, when you pour them together, we're going to have a mixture of two different strong acids. Well, when you do this, we're going to dilute the acid. So we have to use our equation M1V1 equals M2V2 to find the molarity of the final molarity, the M2, of each acid separately.
Yes.
So let's do the HNO3 first. So if I do the HNO3, M1 is 0.00125. That's my molarity, molar. That's M1. V1 is, how much did I have? 54?
54.
Well, now why can I use the volume in milliliters? Why don't I convert that to liters?
Well, we're going to add them together, and they're going to be in milliliters for your V2, so the units just cancel out.
So what's V2? It's going to be 25
79.
plus 54, 79. Now, folks, we got that by just adding the two volumes together. So the molarity of this acid is now 0.0079 molar. Just solving...
Sorry, the one above it.
Sorry, okay.
That's for the next one.
Oh,
8.54 times 10 to the negative 4.
10 to the negative 4. Actually, 5, 4. We can keep the 3 digits, I
Yeah.
think. Okay, and then we would do the same thing for the other acid, the hydrochloric acid, and the M1 is 0.025 molar times my volume, which was 25 milliliters, equals M2 times 79, again, because they're both in the same beaker.
Yep.
And so M2 is...
That one is 0.00791.
Now, what do we do next? That's just molarities. 2
molarities, but if we add them together, then that's our total concentration of hydrogen ions in this solution.
So it would be 8.54 times 10 to the minus 4th plus 0.00791, and that comes out to be 0.00876 molar. Now we're just going to take the negative log of this, and we get a pH of 2.0, I think 2 digits, probably because of the 54.
Yeah.
No, we have 3 digits.
Well,
Look at the problem.
The volumes are all
20. No.
2
there's
sig figs.
2. Yeah. Okay.
Yeah,
54 is
2 sig figs.
So 2.06 is the pH.
Yep.
Okay.
And that makes sense because they're acids, and that's an acidic pH.
Yeah.
All right. One more. This one's a base.
Okay, so we have a base, sodium hydroxide. We have 25 milliliters of 0.25 molar. So to find we can find the hydroxide concentration. Actually, we should make a note. This is sodium hydroxide. Sodium hydroxide completely dissociates into sodiums and hydroxides.
Because it's a strong base.
And he's like, all strong substances completely dissociate. Again, the old high school romances, they all break up. So the concentration of the sodium hydroxide is simply 0.25. 0.25.
Does that 25 milliliters do anything for us there, Mr. President?
You know, that's kind of a distractor, actually. Yeah, they don't need to know that. So
extraneous information.
Extraneous information. If I mixed it maybe in a diluted, that'd be a different thing.
Yeah.
So if you take the negative log of the hydroxide concentration, that's equal to the POH. I would do that first. So
and that gives us 0.60.
0.6?
Yeah, 0.60.
602.
02, okay.
60. And that's equal to the POH. Now, how can I find the pH? The question says, what's the pH?
14 minus that, because pH and POH always add up to 14.
Actually, at 25 degrees Celsius,
Yeah.
Equals, 14. So you just have to take 14 minus 0.6. We could probably do that in our head.
13.40.
That'd be 13.40 equals the pH. And that is a basic solution, a greater pH than 7.
Yep.
So that makes sense.
Answer makes sense.
Totally.
Okay, now we're going to do weak acids.
Weak acids and weak bases. Okay, now, we had this conversation earlier. Guess what? There's this amazing table of them, and this tells you the percentage, or kind of like a percentage dissociation. We'll talk about problems like that, how much they break apart. By the way, the higher the number, what would you say about the acid?
Stronger the acid.
So these are stronger acids, stronger
of the weak.
And these are weaker. They're all weak acids, but the strongest weak acid, at least on this table, is the hydrogen sulfate ion.
Yes.
Okay. So that's kind of where we're headed with this. Okay, now let's do a problem.
All right.
Now we have acetic acid.
Yes.
Now what is the formula of acetic acid?
Well, it comes from the acetate ion, so I'm going to start with an H, C2H3O2.
So acetate is C2H3O2 negative.
Yep.
So the word acid, of course, assumes the hydrogen ion. So we have acetic acid, which is HC2H3O2.
And that is a weak acid, so we do not have 100% dissociation.
How do you know it's weak?
Because it's not one of my 6 strongs.
6 or 6 strongs, yeah. All right. So we're going to now draw a double arrow.
Double arrow.
And we're going to write H positive plus the
So
acid.
we can't just take the negative log of the concentration here because not all of it dissociated. So this is where equilibrium comes into play.
Ice tables have resurfaced on the map. All right, so what do I know? I have 25 milliliters of a 0.25 molar solution. What's up with the 25 milliliter?
Again, nothing.
It's a distractor.
Distractor.
So this is 0.250. How much hydrogen would you have at the beginning?
0.
0 and 0. See,
well, we have it from water.
Yeah, but it's
so small compared to 0.250. We don't
so
need to
this is going to diminish. Since this is 0, this reaction will shift. It's an equilibrium system to the right. So this will be minus X plus X plus X. And then we're going to get 0.250 minus X, X, and X. Now, there's something else that we need to know to solve this problem, Mr. Sams. What would that be?
We need to know the Ka value.
So I'm going to go back to our chart.
Yep.
Okay, you've got it just right there next to you.
Yeah, and I know this one.
I do too.
It's the same as
and
ammonia.
so if you find the acetic acid right here, his Ka is 1.8. So I'm going to write that down. The Ka is 1.8 times 10 to the minus 5. So now I can write that the Ka expression would be equal to the concentration of the hydrogen ion times the concentration of the acetate ion, products over reactants, divided by the concentration of the acetic acid. Now I'm simply going to plug in my values. I'm going to plug in the 0.25 minus X on the bottom, the X's on the top, and then the Ka right here. I'll recopy this. I know this is getting confusing. So I'm going to say 1.8 times 10 to the minus 5 will be equal to X times X over 0.250 minus X. These are all 1-to-1 ratios. And now I need to solve this problem. Now to solve this problem, I want to use my solver in my calculator. So if you're using a TI whatever calculator, you're going to do math and then find the solver. It's actually the 0 button. And you're going to type. Now I really believe in the cross multiplication method. So this times this is equal to, say, the black line is equal to the blue line as it's drawn on the screen. All right, but basically it has to be set equal to 0. So you can say 1.8 E negative 5 parentheses, that's going to do it times, 0.25 minus x, parentheses, and that's equal to x squared. Since I have to set that equal to 0, if I subtract x squared from both sides, then essentially this can just be minus x squared equals 0. So if you type your calculator, this right in here, you solve for x. Now, x is going to be a really kind of tiny number. I know that already. Now, how do I know that, do you think, Mr. Sams?
Well, it's a weak acid, so only a little bit of it is going to dissociate.
And because the Ka is very, very small, 10 to the minus 5 is a pretty small number, it's not going to happen very often, or very, often, maybe not the right word, but you won't have very much dissociation. So what is x equal to, Mr. Sams?
I'm putting that in my solver here, and I get 0.00211.
Now, a warning, when you do these on your solver, oftentimes you're going to get
sig figs.
That you're going to get a number that you may have to scroll over to find the times 10 to the power of something. So just watch that. This one didn't do that. But what is x equal to? We have to kind of go back to our equation.
Right.
X equals the concentration of the hydrogen, and it equals the concentration of the acetate. What was the question again? It says what is the
pH? Should we just take the negative log of our x value?
So then we just say negative log of 0.00211, and that will be
negative log of x is 2.67.
So that's the answer. Now, a shortcut, those in internet land, hopefully you're following, we primarily use TI 80-something calculators, and that's why we're walking through the solver method. But you can also just say negative log of x. Your calculator already knows what x is because it's solved for that, and it stores in it sort of its temporary memory until it gets overwritten, which we'll probably do in just a minute again. Okay, so that's that question. Second question. What is the percentage dissociation of a 0.325 molar solution of formic acid? So first of all, we have to know something about formic acid. So we go back to our cool table guy, and we find formic acid. I hope we have it on here, do we?
It's not. I'll go look it up.
Okay, so we need to know the Ka of formic acid. Our table is not totally complete. Formic acid is HC. We'll figure it out. Hold on. Formic acid is HCO2H. Probably should have given that. Okay, but HCO2H then dissociates into H positive plus CO2H negative. And the Ka, what was the Ka, Mr. Sams?
1.8 times 10 to the negative 4.
Similar to the last one, but 10 to the fourth and minus fourth instead of fifth. All right, now you're going to do the same thing we just did, folks. You're going to say 0.325, 0 and 0, minus x plus x plus x. 0.325 minus x, x, and x. So I can then say 1.8 times 10 to the minus fourth. You'll see that we haven't gotten to the percent yet, but you'll see, is equal to x squared over 0.325 minus x. And when you do the whole solver thing, just as we discussed previously, you just need to figure out how to do this. And it'd be good to pause the video and make sure you get this value. You find that x is equal to what? Mr. Sams is almost there. He's solving it on the calculator right now.
It is 0.00756.
Okay, so that is x. Now, but what is x? Well, it's the concentration of the hydrogen. So if I wanted to find the pH, I could just take the negative log of x.
Could.
But it didn't ask for that. It asked for the percentage dissociation, which means what percentage of the 0.325 broke up. But if you think about that, it is actually the amount that broke up was x. So to do the percent dissociation, you're going to take x divided by your initial amount, which of course will be 0.00756 divided by 0.3325 times 100, of course, for percentage. And you get a what percentage dissociation?
2.33.
So this number is 2.3%, I think. Maybe we do.
Yeah, 3 sig figs.
Yeah, there's 2 sig figs up here.
Oh, yeah, you're right. Probably
so 2.3%. So breaks up to 2.3%. So percent dissociation, this would be important to note. It's basically your x divided by your initial amount. It's actually times 100. So that's how you do those percentage dissociation problems. All right. Okay, I like this question. We have a solution where we have 1 molar hydrocyanic acid and 5 molar nitric acid. Nitrous acid, pardon me. Also calculate concentration of cyanide. Okay, it's quite a long problem. Technically, we have a weak acid, HCN, and another weak acid, HNO2. What do you think we need to do?
Well, figure out which one's stronger. Start with.
You think so? Actually, I
We
wouldn't
can
do it
start
that way.
looking
If
there.
they're both weak acids, I would have to do both problems and add them up.
That works too.
So I would do the HCN first. So HCN, we're going to get redundant here, I think, is going to break apart into H's and cyanides. This hydrocyanic acid was a 1 molar. That's pretty high, probably compared to most. Well, the next one is 5 molar. So 0, 0, minus X, X, and X. 1 minus X, X, and X. And then we look up the Ka value of hydrocyanic acid from the table, which was 6.2 times 10 to the minus 10th, and that will be equal to X squared over 1 minus X. So X for this one, which is equal to the concentration of the hydrogen, right, because that's X right here, is, now Mr. Sams is furiously
Frantically
doing
punching it into my
Mr.
calculator.
Solver Man. He's becoming the expert solver guy.
Mm-hmm.
The solver guy is working very hard on the salvation, not the salvation, the solution to the problem. Mr. Calculator Math.
Ooh, I got a negative. That's not good.
Mr. Sams didn't do it right, so he's continuing to work on solving the solver problem. You make a better guess.
There we go. I got 2.49 times 10 to the negative 5.
2.5 times 10 to the minus 5 molar.
Okay.
We then have to then do a separate problem. This is tedious, I apologize, but it is what it is. The nitrous acid is going to dissociate into the hydrogens plus the nitrite. And this is a 5 molar solution. It'll be minus X, X, and X. 5 minus X, X, and X. So in the Ka of nitrous acid is 4.0 times 10 to the minus 4th will be equal to X squared over 5 minus X. When you solve for X, X is still the hydrogen concentration, and that would be equal to, Mr. Sams?
4.5 times 10 to the negative 2.
So what do we do with these two numbers now, our two different hydrogen concentrations?
Got to add them together.
We simply add them together. And I think I can do this in my head. You know what the concentration of the hydrogen? I'm going to call it 4.5 times 10 to the minus 2. How did I know that?
Well, 10 to the negative 5th numbers are way smaller than 10 to the negative 2 numbers, like 1,000 times smaller.
So if you add these two numbers, this number wins. I mean, it's just huge compared to this number. You know, it's kind of like, you know, if you are standing on the scale at home, and they're weighing you, and I say, oh, let me give you a pencil. What's going to happen to your weight?
Nothing.
It's going to go up a little bit, but the weight of the pencil is insignificant compared to the weight of Mr. Sams.
Yeah. Hey, what are you saying?
Well, you know, you need to exercise more.
I do need to exercise
Yeah.
more. I won't argue with that.
All right, did it ask for the pH?
I believe it does. Yeah.
So
calculate
pH, of course, is just the negative log of this.
Yep. We get 1.35.
And then you get 1.35.
And that's an acidic pH, so that makes sense.
Yep. Mr. Sams is actually not fat. I was just...
But I do need to exercise.
You could exercise more.
Yeah.
Okay, how about
All right.
this one? Okay.
Well, but we also asked for the concentration of the cyanide ions. In that last
Oh,
problem.
it did. So what's the concentration of the cyanide ion?
That would be X from the first problem, it looks like.
So this right here is the concentration of the cyanide ion.
Yep.
You just, boom, right there.
Ta-da, there it
Highlight
is.
in blue. Okay, good.
Okay.
This next question,
page.
which is almost the last page.
Okay, this one we have a mixture of nitric and nitrous acid. Now that one, we have a mixture of a strong acid and a weak
strong.
acid.
And this is weak. Now, we could go back and solve these problems, but I'm going to just tell you folks. Actually, we already have done nitrous acid, although not the same concentration.
No.
You could do, basically, the nitrous acid is going to be HNO2, dissociates into H's and NO2 minus. And this will be the X, 0, X, plus X, X, 0, plus X, X, and this will be 0.25, I'm going that over, sorry, minus X, 0.25 minus X. So you're going to have to have X squared over 0.25 minus X is equal to Ka.
The K value.
Which was a pretty big one, really.
4.5 times, no, 4 times 10 to the negative 4.
4.0 times 10 to the minus 4th.
But guess what?
The other one, the problem with that is the nitric acid,
It's strong, it wins.
it wins. It's going to completely dissociate. So the concentration of the nitric acid from the nitric acid, a little tricky on this one because we are pouring 25 milliliters of each together. So the actual concentration is not 0.25. Actually,
No.
you know what? We made a mistake here. This is going to be what?
That's going to be,
0.125.
yeah, half of that.
Now, how did you do that without doing that M1V1, Mr. Sams?
Well, you just doubled the volume, so you cut your concentration in half.
Yeah, folks, that's an easy thing. If you double your volume, the concentration gets cut in half. So this is just 0.125. So if you take the log of 0.125 or finding the negative log.
Negative log, you get 0.903.
The rule is, guys, is if you have a strong acid and a weak acid, strong acid wins. And you just ignore the weak acid.
Ignore the weak? Yep.
Because, yes, that's it.
Yeah.
Okay. This one's a little bit different. We have a base. So ammonia is a base. Now to do a base, we do have a table of bases. So this is the weak base, or the Kb values of various bases. Ammonia, the one we have in question on this problem, is 1.8 times 10 to the minus 5. Haven't we seen that number before, Mr.
I think so. That was the Ka of acetic acid.
So acetic acid and ammonia actually have the same Kas.
They
Actually,
do.
one's a Ka and one's a Kb.
And we'll
now,
talk about
the
something nifty about
tricky
that later.
part about this is that it's ammonia. So we have to write the reaction. The reaction is NH3 plus what?
Plus water.
Yeah, we're going to say plus HOH.
Because it's a solution.
And it makes ammonium, NH4 positive, plus hydroxide.
Hydroxides, yep.
Now this right here is a liquid, and it will not participate in the equilibrium. It's part of the reaction, but it doesn't participate in the equilibrium. So the ammonia is 0.25 molar. This will be 0 and 0. Notice that I'm skipping the water. So this will be minus x. Here's my ICE. So 0.25 minus x plus x, x, plus x, x. And so the Kb will be equal to the concentration of the ammonium times the concentration of the hydroxide over the concentration of the ammonia. So when I plug in my values, I can say 1.8 times 10 to the minus 5 will be equal to x squared over 0.25 minus x. We then plug that into the solver. We say x equals
0.0021.
Now that's the molarity, but what is that equal to?
That's going to be equal to our concentration of our ammonium ions and the concentration of our hydroxide ions, because those are both of the x's.
And we're trying to find what? The pH,
Trying
right?
to find the pH.
So in this case, you have sort of an additional step. First, I would find the pOH by taking the negative log of 0021, and you get...
You get 2.68.
And therefore, the pH would be 14 minus 2.68,
Yep,
or
11.32.
11.32.
And that makes sense because that is a basic pH.
So you only have this sort of additional step when you have a weak base problem. Okay? And I got the 1.8, by the way, and I'm sure we said this, right here on this table.
Yep.
And I think we're going to do one more.
We're going to do one more with methylamine.
Now we have a different chemical. This is CH3NH2 called methylamine. Now let's kind of make sure the reactions I find are hard for students.
By the way, there's a typo on this chart here.
Oh, is there?
That should be NH3 right there, not NH2.
Oh, this is a typo? Okay, thank you.
It's a typo on your handout, too. Actually, I think it's a typo in our textbook. I recall.
Okay, well, yeah.
Anyhow.
We're using Zumdahl 6th edition, by the way, if you are a internet land person. So we have this methylamine. This is the chemical, by the way, that is the methylamine, and this is his conjugate acid. Okay. One thing I find that students struggle with is writing these reactions. So let's go ahead and write this reaction. So it's CH3NH2. Now when you have one of these N compounds, you want to react with water, and you usually want to react the water as HOH. It's a weak base because it's not one of our strong bases. So this H comes and attaches itself to the methylamine, becomes what we call methylammonium, CH3NH4 positive. So one of the H positives leaves the water. That's the whole, remember, Bronsted-Lowry thing from last time. And then you give off the hydroxide. The water still is a liquid and doesn't count. But it's the same thing. It's point...
Hey, Mr. Bergman. I just realized.
I did too.
That we didn't read the problem very carefully.
Well, we're going to talk ourselves through it. This is 0.25 molar, 0 and 0.
Correct.
We do minus x plus x. Some of you may have figured this out because Mr. Sam's
why are they doing this?
0.25 minus x.
We
x,
just like doing lots of
x.
extra work.
But this, of course, is a what, Mr. Sam?
That is a mixture of a strong base and a weak base.
This right here is a weak base. And this right here, of course, would be a strong base. And what do we learn about strong acids and weak acids?
Strong ones win.
Strong win. So if we have a 0.25 molar solution of potassium hydroxide,
but
we can actually, the amount of hydroxide from here is
negligible.
uber small.
Uber. You got to put the umlaut over the U. Uber. This is the 2 dots, but that's okay.
Is that a 2 dots?
Yeah.
Okay.
There
Well, it
you
makes
go.
a smiley face. Okay. The hydroxide concentration would be, it's a little tricky because we are pouring 25 milliliters together. So this is that division by 2. If you double the
Yep.
volume, the concentration is cut in half. So the hydroxide concentration from the potassium hydroxide, this is from the KOH, is going to be 0.125.
Yep.
I can do that. So therefore, the POH would be equal to, just take the negative log of 0.125.
0.90.
0.90, and then the pH you subtract from 14.
13.10.
13.10. Okay, so we didn't read the problem very well.
Nope.
We apologize
Yep.
because we suck, I guess.
And we wasted 2 minutes of your life that you'll never, ever, ever get back.
How mean and cruel is that? But if you were sitting in class, we'd have...
Could have been even worse. And
It could have
everyone would
been
have gone, and throwing paper at us.
Now you can't.
You can't throw paper at us right now.
How cool is that?
You can send us a nasty email or text message. How's
There you
that?
go. All right. All right. Have a great day.
Yep.
We are the chemistry poets.
Poets. Oh, do we want another
Oh,
poem?
a poem. Do you have a poem?
Nah, let's save it for next time.
Next time.
Bye,
All right.
guys.
Bye.